This video is sponsored by CuriosityStream, home to thousands of documentaries and nonfiction titles for curious minds. Well, the first video of 2020 on this channel was about random things, so I figured I'd make it the last video of 2020 as well. Just some topics and puzzles that never made it in any other videos. So, enjoy. Which of these trips would be faster? A round-trip flight from some point A to point B and back at a constant speed with no wind, or that exact same trip in the same plane, but with wind constantly blowing from point A to point B the entire time? So you can assume the bottom plane would travel at the same constant speed as the top one if there weren't wind. But with it, the bottom plane is going to be faster in one direction and slower in the other. Now, the math here obviously isn't hard, but what does your intuition say? I'm sure many people would assume the times would be equal because the extra boost the bottom plane gets in one direction cancels out the headwind it gets in the other. But using distance equals velocity times time, if we say the distance going one way is d, then for the no wind case we have 2d, there and back, equals some constant velocity times time. And time equals 2d over v. For the wind case, going to point B, you have d equals the same velocity plus the wind, since it's a tailwind making it go faster, times time. So time in one direction would be this. Going the other way, we have the same thing, but v minus w, since it's a headwind. Total time involves adding those two results, and simplifying, we get the exact same thing, 2d over v, except with the wind, we have something extra subtracted in the denominator, making it smaller, which makes the entire fraction larger, so it takes more time with wind, regardless of the speed of the wind. Now that was the technical answer, but you can intuitively think about this using the often useful physics strategy of taking things to an extreme. Imagine the wind is blowing so fast the plane can barely fly in the headwind. Then going one way will be nearly twice as fast, but the trip back will be incredibly slow. You're actually almost at a standstill. So as the wind speed goes up, the boost you get one way does not make up for the headwind you'll get going the other. Okay, now for the how does this affect my life YouTube commenting community, don't worry, this next one is super relatable. Let's say you're in a boat chasing another boat, and your boat is significantly faster, but all of a sudden a fog rolls in, or the other boat puts on its invisibility cloak and immediately changes direction, but not speed. So in an instant, you don't know which way it's traveling anymore, but you know it's going the same speed. The question is, can you still catch the boat in a reasonable amount of time? This is called the trawler problem, and it's another one I first heard from the TV show Numbers.
There's something called the trawler problem, where a fast boat chases a slower boat until the slower boat disappears into a fog bank.
Now pause if you don't want to hear it yet, but the answer is, yes, we can catch the boat without just randomly searching, and here's how you do it. First, we assume we're in theoretical math land where precision is infinite and physics doesn't matter, because with that we can keep track of 2 points which are needed to solve this. One is where the boat you're chasing is located when it goes invisible, and we'll put a dot there. Next, pretend the boat you're chasing has not changed direction, and chase it until you theoretically would catch it, as in go to that point where you would meet had it continued its path. What you do from there is spiral out, using specifically a logarithmic spiral, with that first point we noted as the center. My animator did a good job showing that, but let's go to Desmo so we can see this in real time and make it mathematically precise. So here's the slower boat moving to the right, and it's being chased by a faster boat, which I'll represent as a dot. So the chase is on, but all of a sudden the boat in front goes invisible and changes direction. I'll add in many boats representing the different directions it could be going, but the dot continues to chase as if the boat did not change direction, so keep going to the right until you would have caught it without that change. Now from there, you spiral out using a logarithmic spiral with this equation that has a center of wherever the front boat was when it went invisible, in our case, the origin. The spiral is actually made such that as you go around, your distance from the origin is increasing at the same rate as the slower boat's velocity. And as you can see, by spiraling away, you will guaranteed within one rotation catch the slower boat, regardless of which way it diverted when it got to the origin. Actually, this spiral wasn't even the exact right one, but you get the idea. So there you go. It is theoretically possible so long as the chasing boat is going significantly faster than the other. Next up is an unsolved problem. Actually, several unsolved problems in math that I learned about from my real analysis book. First is a constant called the Euler-Mascheroni constant, and here are the first several digits of that. You get this constant by adding up terms from the harmonic series, 1, 1/2, 1/3, until some 1 over n. Then you subtract the natural log of n, that last denominator. And as you let n approach infinity, you get the Euler-Mascheroni constant. Visually, you can think of this as the area of a bunch of rectangles starting at x equals 1 that all have a width of 1, but whose height decreases according to the harmonic series. So first has a height of 1, then 1/2, 1/3, and so on, approaching 0. But we only take the area that lies above the graph of 1 over x. The total area of the pieces of rectangles sticking out above that curve, so everything you see in green going out forever, is the Euler-Mascheroni constant. The unsolved part of this is we don't know whether this number is rational or irrational. We still don't know if this number ends or has some infinite pattern somewhere down the line. I don't think I had heard of a number where we weren't sure about whether it's rational or not, but there are actually several. We know that e and pi are irrational, but we do not know whether pi plus e is irrational, or pi minus e, or pi times e, or pi over e, pi to the e, or several other combinations of these two. That surprised me. And these are some of the few unsolved problems in math that can be understood by someone who doesn't have a degree in math. And this last one I came across when researching the Hypersphere Universe video from several months back. As mentioned in that one, since we really can't imagine our entire 3D universe curving in a higher dimension, it's often necessary to make comparisons to a flatland creature living on a sphere. Basically take everything down a dimension to understand what we would or theoretically could experience with curvature happening in a dimension beyond the 3 we know. This one was very theoretical, but a cool thought experiment. So let's say you're a flatland creature living on a sphere and a very stretchy fence is placed around you, like you're in flatland jail. Now, would you say the creature is inside that fenced region? I think that's fair to say. This is the interior, right? But I said this fence can stretch, so let's inflate it a bit. Now would you say the creature is inside? What about now? Remember, this fence is confined to the sphere, that's the universe, so it will continue to increase in size until it reaches a maximum circumference. This is called a great circle. But after that point, by pushing the boundaries out more away from the creature, the region starts to get smaller. And then you eventually get to a point where you're kind of outside the fenced region. But this makes you question if there even is an inside or outside. But now take this up a dimension. If we lived on a hypersphere and were enclosed by an infinitely stretchy balloon, we could inflate the balloon normally. It would increase in volume as we kept inflating it. But just like in the flatland case, it would eventually reach a maximum volume, with a radius matching that of the hypersphere. And as we kept inflating it, the balloon would enclose a smaller volume, eventually getting back to its original size, with you, quote, outside of it. So theoretically, in a hypersphere universe, you could sort of escape from an infinitely stretchy balloon. And you can thank me later. Alright, I'm going to call it there because I'm taking a mini holiday break, but for more random things involving math, science, and even higher dimensions, you can check out CuriosityStream, the sponsor of this video. This documentary called Stephen Hawking's Favorite Places is definitely one of my top choices when it comes to these theoretical physics concepts, not just for the information, but for these very impressive visuals. It's 3 videos narrated by Stephen Hawking, which show him going on a journey through space while he discusses some big ideas like black holes, parallel universes, quantum physics, and plenty more. This series covers some of the history of the universe and also some of the biggest current ideas in physics and cosmology. And they have an entire category of their site dedicated to space and the universe, which is my favorite category of documentaries to watch. CuriosityStream is available on a variety of platforms worldwide, and it only comes out to $2.99 per month. But if you sign up by using the link below, you'll get your first month's membership completely free, so no risk in giving it a try. And with this, you'll have unlimited access to top documentaries that I'm sure many of you will enjoy. And with that, I'm going to end that video there. Thanks as always to my supporters on Patreon. Social media links to follow me are down below, and I'll see you guys in the next video.